Welcome to today's Explainer. We're taking physics back to its absolute basics right now. We are going to decode the fundamental language of how we measure the entire universe. Look, whether you're building a bridge, launching a rocket, or honestly just trying to figure out how fast you're driving down the highway, there is this hidden architecture to the numbers you're using. And today, we're going to uncover exactly what that architecture is. So, have you ever actually stopped to wonder how scientists can measure literally everything, from a tiny, vibrating atom all the way up to a speeding car, using the exact same underlying concepts? I mean, it kind of feels like magic, right? But it's actually a highly organized, brilliant system of information. To truly grasp physics and mechanics, we really have to start by asking, how do we actually put a real number to physical reality?
All right, let's get right into it. The whole thing starts with physical quantities. Now, that's just a formal scientific term for a property of a material or system that can be quantified by measurement. To put it simply, if you can measure it and slap a number on it in physical reality, it's a physical quantity. Boom, that's it.
Chapter 1. The Fundamental Base Quantities.
You can kind of think of base quantities as the independent variables of the universe. They are essentially the foundational Lego bricks of reality. They stand entirely alone, and you absolutely cannot reduce or break them down into anything simpler. You can't explain a base quantity by pointing to another quantity. It just simply is what it is.
When we boil it down, the foundational big three base quantities that we use to construct almost everything else in mechanics are mass, length, and time. Mass is measured in kilograms, length in meters, and time in seconds. Now, if you look at the fundamental standards, a meter was actually redefined by the distance light travels in a vacuum, and a second is technically defined by the oscillation of a cesium atom. But for our practical purposes, just remember this trio: mass, length, and time. They are your ultimate foundation.
So here is the absolute crucial distinction to wrap your head around. Base quantities are your independent fundamental blocks. Derived quantities, on the other hand, are entirely dependent. They don't just exist on their own out in the wild. They're combined structures that we create by stacking those base blocks together using math.
Chapter 2. Creating derived quantities.
A derived quantity is, well, exactly what it sounds like. It derives its very existence from the base quantities. You literally create it by combining those base blocks through basic math, specifically multiplication or division. Basically, you're taking the big three and snapping them together to create a brand new concept.
Let's look at how this math actually plays out in practice. Take a complex idea like velocity. It's practically just a length divided by a time, literally meters per second. Or if you want volume, you just multiply length by length by length to get cubic meters. Want density? Easy. Just take your base mass and divide it by that derived volume we just made. It beautifully shows us exactly how the basic alphabet of physics creates really complex words and sentences. Picture this practical example. Imagine you're pushing a really heavy box across the floor. You are taking a base quantity, which is the mass of the box, and combining it with a derived quantity, the acceleration you're applying to it. When you multiply that mass times acceleration, you create an entirely new derived concept called force. Now, we measure force in newtons, sure, but under the hood, a newton is really just kilograms multiplied by meters per second squared. It's literally all just base blocks.
Chapter 3. Checking the math.
Okay, so if we're building these complex equations out of basic blocks, how do we make sure our math is actually right? The answer is this brilliant tool called dimensional analysis. You can really think of dimensional analysis as basically a grammar check, but for physics equations. Just like you can't have a coherent sentence without a verb, you cannot have a valid physics equation where the underlying base dimensions don't balance out.
This grammar check involves three super simple steps. Step 1, you identify the fundamental base dimensions in your equation. Remember, that's usually our good friends length, mass, and time. Step 2, you treat these dimensions exactly as if they were simple algebraic quantities. You can add them, subtract them, multiply, and divide them. And finally, step 3, the golden rule. You make absolutely sure the left side of your equation perfectly matches the building blocks on the right side. If you have length divided by time on the left, you better have length divided by time on the right. Otherwise, the math is broken.
Chapter 4. Real-world applications.
So why does all this matter outside of a physics classroom? Well, whether you're using a standard ruler to measure wood for a weekend DIY project or marking a hem on clothing, you are interacting directly with the base quantity of length to ensure fundamental accuracy in your real life.
And this right here is exactly why unit conversions are such a big deal for derived quantities. When you cross a border,
A derived velocity of 80 kilometers per hour expresses the exact same physical reality as 50 miles per hour. If you can't translate those length over time blocks correctly, you might just find yourself with a hefty speeding ticket.
Which leaves us with a pretty fascinating final thought to ponder as we wrap up this explainer. We've seen how absolutely everything we measure relies on these fundamental base quantities of mass, length, and time. But if the very fabric of our universe somehow shifted tomorrow, would our fundamental building blocks still be enough to explain it all? Or would we need to discover entirely new base quantities to measure our strange new reality? It's a wild thought to leave you with. Thanks for joining me on this deep dive into the building blocks of measurement. Keep questioning everything, and I'll see you in the next one.